Welcome back to part 3 on complex zeros. In example 4, we have a polynomial f of x, which is equal to x to the fourth minus 3x to the third plus 6x squared plus 2x minus 60. Given that 1 plus 3i is a zero of the function, find all the zeros. This was my big hint. I know that x equals 1 plus 3i, and that is one of my zeros of the polynomial. Therefore, I also know that x equals 1 minus 3i because complex zeros always come in conjugate pairs. That means that x minus 1 minus 3i is one factor, and x minus 1 plus 3i is the other factor. I'm going to treat the x minus 1s as the first term in a perfect square trinomial, and then I'm going to FOIL using first outer inner last multiplication, where x minus 1 times x minus 1 will give me my first three terms. That will give me x squared minus 2x plus 1. And then the inner and the outer will add to 0 because of the plus minus signs here. And so my last term will be a minus 9i squared. Simplifying further, I have x squared minus 2x plus 1 plus 9. So finally, I know that one of my large factors with real coefficients is going to be x squared minus 2x plus 10. So now I can find the other two factors of the polynomial f of x using long division, or I can graph it. I'm going to graph it first because if I can find what those other two factors are without having to do anything crazy, I'm just going to do that. So x to the fourth minus 3x to the third plus 6x squared plus 2x minus 60. And it looks like negative 2 and 3 are the other two zeros of the polynomial. So I'm going to check x equals negative 2 and x equals 3. So let's check to see if this works. If I have 1, negative 3, 6, 2, and negative 60, and I use synthetic division, I should be able to show that one of the factors is x plus 2. So dropping the 1 down, negative 2 times 1 is negative 2. Negative 2 plus negative 3 is negative 5. Negative 2 times negative 5 is positive 10. 6 plus 10 is 16. Negative 2 times 16 is negative 32. 2 plus negative 32 is negative 30, and negative 2 times negative 30 is positive 60. And sure enough, that is a factor. Negative 2 is a zero of the polynomial, so I know that f of x, one of its factors so far, is going to be x plus 2. Again, when I set this equal to 0, I know it will be a negative 2. So now I'm going to recycle my polynomial using 3 as my root this time. And I'm going to hopefully show that 3 is another zero of the polynomial. Dropping 1 down, 3 times 1 is 3. Negative 5 plus 3 is negative 2. 3 times negative 2 is negative 6. 16 plus negative 6 is 10. 3 times 10 is 30. Negative 30 plus 30 is 0. So once again, I showed that 3 is a zero of the polynomial f of x, And so one of my factors is x minus 3. Now the question is, does the remainder in my second synthetic division show that it matches what I had when I found the quadratic that represented my two complex zeros? And it does actually work, which is all so good. It all fell into place because this is my x squared term, this is my x to the first term, and this is my x to the 0 term. So my other quadratic term would be x squared minus 2x plus 10. Now, if this had been a factor completely, then you would leave these as their complex binomials. Most of the time, textbooks will ask you to leave it in integer coefficient form or rational coefficient form.